All right, so here we are with -2 cosine theta plus 2. And what we're interested in is we want to find, what should we want to find here? We want to find the leftmost point. We want to find the leftmost point of the cardioid. How are we going to find the leftmost point? Which is right here. What's the principle here behind this? That's the rightmost point. So we want to find the rightmost point. We know the leftmost point. What is the leftmost point? So it'd be 4 pi, right? You say 4 pi. Or in rectangular coordinates, 0, -4. We want the rightmost point of this cardioid. And what's the approach to get the rightmost point? Yeah, so we want, as theta changes a little bit, we want x to not change, right? So that means that derivative of x with respect to theta is going to be 0. What if we want the highest point? With the maximum? dy d theta equals 0. Okay, but so we'll just go for this leftmost point here, right? So dx d theta equals 0. Okay, and so this is, it kind of gets, the trig and the algebra gets a little involved here. So I'm going to go fast, and if I lose you, you're going to have to watch the video because we got to get to area, okay? So here we go. X equals always r cosine theta. And so what is it for this one? What is r? -2 cosine theta plus 2 cosine theta. So that equals -2 cosine squared plus 2 cosine theta. And that's what x is always on this cardioid. It's always -2 cosine squared theta plus 2 cosine theta. I just substituted in our r function for r times cosine theta. That's what x equals, right? R cosine theta. All right, so here we go. dx d theta equals 0 means taking the derivative of this with respect to theta. So we're going to get, what is this? Cosine squared. So it's going to be -4 cosine to the first times derivative of cosine. Negative sign. Chain rule, right? Chain rule plus -2 sign. We want that to be 0. Oh, this is fast. Good. So I was thinking of something else that was involved. All right, good. So now we want to solve this for 0, which is simply a matter of what? Factoring out sine theta. So sine theta. And so let's factor out negative sine theta, so our inside is nice. So negative sine theta, so it leaves us with 4 cosine theta plus 2. Oh, there's a negative, right? There's 2 negatives, right? So this is negative. Should have done positive, but here we are. Okay, so what does that mean? So sine theta could be 0, or I'll go ahead and take the opposite. 4 cosine theta minus 2 could be 0, which means cosine theta could be 1/2. Okay, so this is giving us lots of angles, right? And all these angles should have dx d theta equaling to 0. So what about this? This is theta equals 0, pi, 2 pi, etc. Now looking at the graph, which one applies here? What angle applies to our situation? Nope. Yeah, look at what's happening at pi. You see pi? Pi has a dx d theta of 0. Missed. Vertical tangent, right? Vertical tangent is dx d theta equals 0. So that's at x equals theta equals pi. Okay, so these are definitely not 0, 2 pi over here, so this must be what? Cosine theta equals 1/2, which just means theta equals 5/3. And? Yep. In the fourth quadrant. Or anything plus 2 pi. Either of these plus any multiple of 2 pi. So negative pi over 3. Yeah. Negative 5 pi over 3. What is this? This is 6 pi over 3. 7 pi over 3, etc. Okay, so we found it. Question? Yeah.
Will a polar function like this have a domain restriction given so that we know which value to have provided the domain, or is it just sort of like just a general value?
Yeah, so yes, if it had a restriction, then you would pick the one that fell in the restriction. If it didn't, then you would specify, for instance, pi over 3 plus 2 pi k, where k is any integer. Okay, so this is the, what is this? This is the point then. We know theta is pi over 3. So how do we get r? What is that r value for that? Anybody? Right, so it's gonna, right, so this is the function, r equals negative 2, this is our function, which tells us a value, the value of r for every value of theta, right? So you're gonna plug pi over 3 into this, and you're gonna get, is that just 1? You get 1, so negative 2 cosine pi over 3 plus 2, like Pharaoh said, and then you get 1. So that's 0.1 pi over 3. Okay, so what if you wanted to find the equation of a tangent line? So let's do this. What about the equation of the tangent line at 5 pi over 6? This is going to be, so we're going to need the rate of change in terms y and x, or the slope. So we need dy dx. And how are we going to get dy dx? It's the same kind of idea as in parametric. We're going to do. We don't have y as a function of x. That would be it's very either impossible or very inconvenient. Okay, this is much more convenient as a polar function. So to get dy dx, we want dy d theta over dx d theta. We already did dx d theta. What is it? This thing, 4 cosine sine minus 2 sine. Okay, and then dy d theta would be from r sine theta, right? So y is r sine theta. And that would be negative 2 cosine theta plus 2 times sine theta. So we're going to find dy d theta. We're going to put it here, and then we're going to evaluate that. So it's so we have dy dx as a function of theta. So we're going to evaluate that at 5 pi over 6. And that's going to give us, right here, that's going to give us the slope of the curve right there, or the rate of change of y with respect to x. And then if you want to find the equation of the tangent line, so that would be the slope of the tangent line. To find the equation of the tangent line, then you would need that point. How are you going to get that point? We know that theta is 5 pi over 6. How do we get x and y? X equals r cosine theta, y equals r sine theta. So we would evaluate r, we'd evaluate cosine and sine, we'd find the coordinates x and y, and then you'd have the slope from dy dx, and you'd be home free. You could write the equation of the tangent line, which you've done in the past. So you get that. There's your point, and there's your slope. So I'm not going to finish for time's sake, but do you see the roadmap to finish? Can you do it? It's a lot of just plugging and getting all the numbers from this point. Okay, let's do area then. So here's the idea with area. We have, here's the buildup. So we have some function here. And this is r is some function of theta. And we have a starting angle, theta 1. And some ending angle, theta 2. And so we think about area in rectangular coordinates. And what was it? It's from the function to the axis of the dependent variable, right? Okay. So from the function to the zero value of the dependent variable. So if we go from the function to the zero value of the dependent variable, we're really talking about something like a slice like this. So in rectangular coordinates, we summed up typical rectangles. What are we summing up here? Typical, what are those? What are those that's supposed to be? It's a little wavy. Here, I'll fix it. Right, and what shape is that? Is it going to get worse or better? Slightly better. Not great though. Okay, not bad. Okay. So what shape do we have? Triangle. So our typical piece when we're going to find areas in polar coordinates, it's going to be typical triangle. Area of the triangle is 1/2 base times height. Okay, so the base, this is this dimension here. And the height is going to be, what will the height be? R, the current value of R. All right, so we have 1/2 base times R, first of all. So what is that base? Okay, so that base, we're going to do that actually by little circular arcs that are trying to be like the polar curve. Okay, we're going to do circular arcs that are trying to be like the polar curve. So what is the length of a circular arc? So let's review that. And you should have done this in Clara. Right, so if you have an angle theta, like this, and the radius is capital R, what's the length of your arc? Capital R theta. Okay, so B is little r, and what's the angle? D theta, right? Or yeah, delta theta. So the base of our triangle is going to be by your circular arc formula, the length of a circular arc. It's going to be the radius times theta. Well, now we're talking about a little change in theta, right? So for our little typical strip, we have a delta theta times the radius gives us base. So therefore, our strips are going to be 1/2 r delta theta times another r. And then as things get small, right, so delta theta is going to go to 0. Our dA is going to equal, what, 1/2 r squared d theta. So our typical triangular slivers that are going to fill up from the curve to the pole, it's always going to be like that, from the curve to the pole. Each one of those has a little area of 1/2 r squared d theta, which is really the area of a triangle. Do you see it? So the area of this whole thing then would be integral from theta 1 to theta 2, and we're going to sum up all the little triangular slivers. 1/2 r squared d theta. And what is r? What is r? That's changing, right? So that's why we need integration, because that r is changing dependent on theta. So theta 1 to theta 2, 1/2 f of theta squared. It's the same as saying this. So does the build-up make sense? So then we'll look at some examples here. But that's so what we just did, very consistent with what we did lots of the semester, right? If we want an area, then we're gonna what? Take a typical little bit of area and then we're gonna add them all up, right? We've done that all semester. That's what an integral is about. Right, okay. So this other one. So we got a couple functions we want to look at here. 5 cosine theta minus 2 and cosine theta plus 1. So we're not going to take the time to do those. That would be good practice, but we're just going to go for it here. So I'm going to graph those at the same time. So you can determine which is which. So which one, f of theta is 5 cosine theta minus 2, g of theta is cosine theta plus 1. Which is which? What do you think? Blue one is F. That's right, because it's going to start at 3. Red one is G. Let's put those there. Okay. So the blue one is F, the red one is G. Okay, and so I want to calculate this area here. Let's see. Pretty turquoise. I'm going to calculate that area right. No, I don't. I want to calculate all that shaded region right there. I want to calculate all that shaded region that I'm showing you. So what would that entail? How am I going to calculate all of that shaded region? So remember how these work. The integrals, what? It's like summing up little, real skinny triangular wedges. Every vertex of those triangles is at the pole, right? So as you sweep around counterclockwise, you're sweeping out area. Okay, so how can we set up an expression that would calculate that area? So let me give you a hint. So here's a typical strip. That's the best typical strip I've drawn all day. Okay, so that's our, little dA. How am I going to get the total area of, or delta A, I should say? Total area of the turquoise shaded region.
You want us to define theta 2?
What's that?
What's the angle?
Okay, it's the right question, right? So we need this angle, right? So we need this angle. What is this angle right here? So what's the starting angle? That's easy. Theta 1 is 0. Okay, and so what defines theta 2? Where they intersect. So we need the angle at which they intersect. How are we going to get that? They have the that's the angle where these two curves have the same value of r, right? So we're going to set the r's equal. We're going to set r's equal because we want the angle for which r is equal on both these two graphs. You know, you never set equations equal. That doesn't make sense. You can't set equations equal. But what we do want to set equal is the values of r. We're going to set values of r equal to get the corresponding theta. So 5 cosine theta minus 2 equals cosine theta plus 1. So what do we get? Cosine theta is 3/4. Arc cosine of 3/4. So arc cosine 3/4. All right, can you set up the expression for the turquoise area? Can you do it? So it's going to be an integral from what to what? 0 to arc cosine 3/4. And now the question is, what goes inside here? What are we going to have? 1/2. So does it have to do with both of them or just one of them? All we care about here is, so what's defining the outer edge of this region is just f. So g really doesn't play in except for getting that intersection point. So yeah, we're going to have 5 cosine theta minus 2 squared d theta. That's it. That will give us, that integral will give us that area. Okay, now I want the turquoise region. Turquoise only. How am I going to get that area? So what will that be? Same thing, but? So it's the exact same thing, but g of theta? So but I want the turquoise. I still want the turquoise. Okay. Yeah, so this is kind of like, we've seen this before. You've got outer function. So what used to be like upper function and lower function in y and x. This is like the area between curves, right? So before you had like y1, y2, and to get the area between, what our typical strip was, had a height of y1 minus y2. And so we did the integral y1 minus y2 dx. So now you just have to imagine, instead of up and down, it's kind of out, right? So it's out and in from the pole. So the furthest away from the pole is like our kind of like our y1, and the closest into the pole is kind of like y2. So we're going to do, for this one now, we're going to do the same bounds, theta 1 to theta 2, 0 to theta 2. And we're going to do 1/2 what, f theta, so I'll just write f theta squared minus 1/2 g theta squared. Don't do f minus g quantity squared. That's not right. Because that's a different function. F minus g is some new function. Okay. So we need the area out to function f minus the area out to function g. Okay. F minus g is some other function that's going to have its own different area to the pole. Okay, good so far? Okay, so here's the fun part. If that wasn't fun. Any questions on that? So now Okay, so now we got this. Here, now I want a new region. I want this region with corners this here, 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 like that. I want there, that area. Brady. Oh, okay. Yeah, no, that's actually absolutely the right way to think about it. You got to think about sweeping and what happens when you sweep, and thinking about these functions as you sweep. Christiana. Okay. Okay. So first the red graph, then the blue graph. Okay. So then you want to subtract. How are you thinking of it? I mean, if not subtract, then what? Right, but then that'll give you two different numbers. They'll give you, so then what? There was a hand over here. Okay. 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 Red minus blue after that. John. Or just blue, okay? John, what do you think?
Well, I think mine's like an inefficient way to do it, but I would have broken it up into 4.
Okay.
And found the area of the blue curve until the intersection, sweeping from 0 to the intersection, and then I would have done another integral to find from the intersection to pi, and then you'd have one that you would subtract, and then one that you would add.
Okay.
But,
Yeah, that might work. So so watch this. This will really help you to see what to do. Ready? Watch. What would that be? How would we get that much area? Just the area of G, right? The area of G from 0 to that intersection. And then starting from there, so there were some good answers when we were having a discussion. Some of you got it, right? So as the angle changes, we really just need all this angle in from, or all this area in from G to the pole until this intersection, and then starting the intersection, we need the area in from what, F to the pole. But then we're going to need what? We're going to need this angle, right? This angle is not pi over 2. How do we get that angle? So what's this? This is like theta 3. This is theta 1, theta 2, yeah, theta 3.
we just need to find when the blue curve equals 0.
Right. So we need the radius for the blue to be 0. So that's going to be, where's 5 cosine theta over 2 equal to 0? Arc cosine of? Okay, so let's write down the integral and then we can go. So everyone see that that's the, okay? And so then the area of this region is going to be a sum, right? Because the angle just keeps going. And the first part of it, we're going to integrate according to the G curve. And then starting here, integrate according to the blue curve. So it's going to be integral from theta 1 to theta 2, which is our cosine of 3/4 of what, G? Plus the integral from theta 2 to theta 3, this one we just found, where this blue curve equals 0, 1/2, and that's F. So you really have to think about the top of the curve is the radius, right? And then all this area is coming in slivers to the pole. And how you gonna frame it to get it equal? All right, so Tuesday night, the final is in BAC 316. I will post that on Blackboard. BAC 316. I'll see you at 7 p.m. I will on Blackboard and through email. I'll give you all information about preparing, different practice problems, outlines, and review sessions Monday and Tuesday. So just watch your email, watch Blackboard. That will all be up hopefully this afternoon.